No, it just shows the blue screen. Yeah.
Yeah, it doesn't recognize. It doesn't recognize.
When you leave.
Something I'm going to. Yeah.
You're my classroom?
Almost there. No, well,
Not yet? Oh, you don't. Oh, for the book.
Well,
Maybe stop.
no, I think your adapter is not good.
Yeah,
Okay.
anytime I'm sitting like, okay.
Which laptop belongs to? You know what? I try different adapter. I try different. Can your adapter again?
Yeah, let's try maybe.
Okay.
I have
Good afternoon, everyone. Welcome to the first ACEAS seminar this year. I'm Max Nikolash, and I'm one of the seminar organizers. We have a new team now, so I'm based here at UTAS. Rebecca McGeer and Timur Sohail are the organizers at ANU and UNSW. So this seminar is streamed to ANU and UNSW. So if you have any suggestions for speakers for this year, please contact one of us. So I would like to start with the acknowledgement of country. So on behalf of the University of Tasmania, I acknowledge all countries participating in this meeting and also acknowledge their elders, ancestors, and their legacy to us. I would like now to invite the director of ACEAS, Professor Martin, to introduce our speakers.
Thanks, Max, and thanks to everyone joining in person or online. It's really great to have you here for this, which is going to be a tremendous seminar. I'm committing you to that, Robin. A tremendous seminar for the start of the year. Robin, I think, arrived in Hobart on a yacht, and I was informed via Twitter that she was sailing up the Derwent from someone who's in San Diego. But there's great enthusiasm to have Robin here. There are lots of people who are really very excited to hear that she was going to be here on a Fulbright, working with Steve, or hosted by Steve Rintoul, and she'll be here for a number of months. So this is great to have Robin give a seminar really early on in her stay, and she'll be very available, I'm sure, and very enthusiastic to talk to any of you about any of her interests. Robin's based at Lamont Doherty as part of Columbia University. She's been there for a very long time, a good while, and she's a real pioneer in Antarctic ice sheet things, most generally, especially around geophysics, airborne geophysics. But perhaps more recently, I think, taking that all the way through to coastal impacts, coastal change, working with Indigenous people in Greenland, and really trying to understand the pointy end of sea level and the impacts it has on people, and helping them to make decisions and adapt around those things. She's got a real enthusiasm about her. I'm sure you'll detect that. So I'm really excited by this seminar. And so I'd like to welcome Robin Bell up. Come on up, Robin. Thank you.
Well, thank you, Matt. And thank you, Steve, for making it possible for me to be here. And thanks everybody who's made me feel very welcome here. It's been a wonderful opportunity. I'm going to cover a couple things today. I can never really talk about one thing. So I hope to do three things today. One is let you know what the Fulbright I'm here on is, give you a little bit sense of my science background. Maybe I'm for four things, sorry. Tell you about some work in ice shelf, interdisciplinary work on the Ross Ice Shelf in particular, and then maybe start to engage you in some of the thinking I'd love to prompt, engage, foster here about East Antarctica and the vulnerability points there. So we'll see if I get through that. I'm here as a Fulbright Distinguished Chair. I recommend anybody try to apply for one. Steve and I managed to put together a successful application in about 4 days, so it can be done. I proposed that I wanted to help advance the design of international collaboration and changing ice in East Antarctica. I was involved with planning the International Polar Year 2007 to 9 and was lead scientist on the AGAP project. So I'm deeply committed to the role of international science. And I also helped launch through the US National Academy the Thwaites Project. As Matt said, I'm very keen to learn how the work being done here with communities impacted by changing shorelines. And I'd love to share my experience in working on diversity in the science. So since I love to talk about things other than ice shelves, I thought I'd just give you a quick like snapshot of other things that I'm happy to talk about with anybody. You know, and I'll just I'd cover some of these, like water beneath ice sheets and ice hydrology. You know, just some of the things I've done that, you know, might catch people's eyes. That, you know, the ice in Lake Vostok isn't stagnant. It actually melts and then refreezes, and there's a real circulation system in Lake Vostok. You can see that in the stratigraphy and also in the ice cores. It's recorded in the structure of the crystals there. Then moving on to AGAP results, we discovered there that the rivers there flow uphill, that the way the ice sheet drives the water, that the water flows in the river valleys uphill in the gambrets of mountains. And even cooler, I think, this uphill flowing water refreezes to the base of the ice sheet, thickening the ice sheet from below. And I meant to put a local picture here, but if we were to be standing here looking up at Mount Wellington, the peak in this radar image, so this is the surface of the radar, the surface of the ice sheet in that black and white image, the white line, the wiggly brown and white line at the bottom, that is the base of the ice sheet. The layers are what we normally think of and what Neil would like to drill and sample. And then there's this big blobby thing coming up. That blobby thing is about as tall as Mount Wellington is. If we were standing here, it would be that much towering over us, about 12 kilometers long. And that's all water refrozen to the base of the ice sheet. So just changing the way I thought about ice sheets and how they're structured. It happens in Greenland too. Turns out when Icebridge flew over Greenland, they found all these weird structures, both on the edge and in the middle. And Renee, I'm sure, knows the story that when they first identified these, they thought there were mountains underneath the ice sheets. Thank goodness we had gravity. We could show they were not mountains. They're made of ice. I'm also very keen on surface hydrology. This is work we did where we demonstrated that water flows onto ice shelves and also off them. And that, you know, we think of lakes as being the critical part of ice sheet hydrology. But when we look around here and the life we live, we know that we have to consider more than just lakes as part of the hydrology on ice shelves and what can happen in the future. And we demonstrated that these have been active since 1912. Here's somebody who's walking through an ice sheet hydrology in 1912, barefoot. I'm not sure what we're thinking. And then finally, some recent work we did actually showed that these ice shelf rivers can carve through the ice shelf. This is one you all carry the image on your left, on your iPhone. It's in the Google Images. You zoom into the front of Petermann Glacier. That beautiful image of sea ice on an ice shelf is on your phone. And it actually shows that there's an estuary there, that the water is actually flowing and the ice are flowing up that river onto the ice shelf. And it's actually managed to carve and fracture the ice shelf on Petermann and on Ryder in the north of Greenland. So these are just some things that I get excited about. I also recently, during the pandemic with Kirsty Tinto, launched a program called Greenland Rising, where we worked with the Greenland Institute of Natural Resources based on work we'd originally done in the Hudson River, mapping benthic habitats. We're actually working with communities who are experiencing really rapid sea level change. It's rapid, but actually the sea level's falling because of the rebound. That these islands are coming up out, places they can no longer navigate through because of the channels getting shallower and shallower. And so we've been working with 3 different communities on what are their priorities, what matters to them, and how are they going to adapt in the future to the rapidly changing sea level around Greenland. And one other passion of mine is diversity. It's, you know, in my feeling that it's really essential in science. You know, the research shows that science is better when we have a more diverse group of people around the table. As I like to say, our ideas are stronger, they're tested. You know, we all know that if you test something from different angles, you're going to end up with a better product. I'm motivated by the brilliant women I've watched flee science due to toxic environments, So I've helped change the environment at Lamont through a significant funding with NSF. I was part of the team at AGU that led AGU to determine that scientific misconduct was equivalent to bullying and harassment, and you couldn't serve on a committee or get a medal or an award if you'd been if you had accusations of bullying and harassment. I developed anti-racism plans with metrics of success, and recently funded a program to address racism in science, particularly geoscience. So an astrophysicist friend of mine said, you know, remember you have two jobs. You're trying to pull off. You're trying to be a scientist and work on diversity. But I'm happy to talk about the three things that I think are important to foster institutional change, be an ally or an advocate to people in the minority, if necessary, figure out how to provide them armor, directly confront toxic environments. Waiting and watching them doesn't do any good. I'm happy to have further conversations here with leaders and future leaders, whether it's lectures, workshops, or reading seminars. I watched change happen by bringing it to the forefront. So now we're going to go on to what I was supposed to talk about, which was ice shelf vulnerability. And this was work where very much led by Kirsty Tinto and a multidisciplinary team from institutions across the US and our New Zealand partners. And just to remind you, it took 15 years to get funded. So sometimes you have to try many times to get an idea across. So we're going to look at the Ross Ice Shelf. That's where this work is focused. And we're going to look at how it's really an interdisciplinary problem. And you'll see by the end of this why I think that the most fruitful way to look at East Antarctica is really to try and figure out how to bring disciplines together and look at it in an integrated system science fashion. So let's just start with we're going to look at the Ross Ice Shelf. We're going to look at ROSETTA, which is the acronym for the project. It was the 15 years ago acronym, so it doesn't make sense anymore, but it's a beautiful acronym, so we kept it. And then we'll look at what we learned and its long-term stability. So we're really going to try and look at the glaciology, the ice shelf structure and history, the geology, how it controls the stability of the ice sheet shelf, and the oceanography. And really the motivation is that we know that the ice shelves are changing, they're melting, and they're calving, basically losing mass. And we're going to focus down here today on the Ross Ice Shelf. One that's considered one of the large, cold, but relatively poorly studied. And we're going to look at those interactions between the ocean, the bathymetry, and the overlying ice shelf. It's considered cold and stable, but there are places that are vulnerable, and we certainly know that that's where, you know, many of the early expeditions went across the Ross Ice Shelf and considered it the easy part of their travels. We can see that it is fed by both East and West Antarctica. And if we zoom out, we can see how much sea level feeds into it. We typically think of it only getting ice from East Antarctica, sort of that Icepod coast, but it also gets a significant amount of ice from East Antarctica, that big catchment, that basically 9 meters, almost 10 meters of sea level from East Antarctica feeding into the Ross Ice Shelf. So its fate is important in terms of where it sits in terms of both East and West Antarctica. Glaciologically, it takes about 1,000 years for a piece of ice to go afloat on the ice shelf and then get to the front where it calves off. What we see today may not be what's happening in the past. We know that ice streams, the glaciers that flow in and feed it, have turned on and off. And in that, you can see it actually in the way that ice shelf is put together. It's kind of like you stop putting different building blocks in, so you can see that there are places that different of the ice streams are missing. If you were to zoom in closely here, you would actually see there are loops in the structure, and the loops are actually placed times where different ice streams coming out of West Antarctica turned on and off. So we're also going to look at the oceanography and the role it plays, how it transports the heat both into the ice shelf and to the grounding line. And we're going to look at what's controlling that bathymetry and the roughness in the ice shelf cavity underneath. So there we got the oceanography. And then just because this actually did start as a geologic project, the other real question is what are the geologic structures underneath the Ross ice shelf? When I was a graduate student, all the lines were simply drawn from what people had learned from driving in the Ross Sea to what they speculated was underneath the ice sheet. So there were just these beautiful parallel lines to the Transantarctic mountains. But there's a real question of where do we go from, the rocks that are similar to the rocks in Australia, sort of the old East Antarctic craton, the modified material that makes up the Transantarctic mountains, the Ross Belt, the Beacon, and the Farrar, things that would be, if they were exposed, would be very familiar to you as landscapes. And then East Antarctica, West Antarctica, the part that was stretched and pulled when Gondwana broke up. But what we really didn't know before this project was where did the geologic boundary between East and West Antarctica go? It was really easy to say, it's right there at the Giant Mountain Range. The Giant Mountain Range is kind of obvious. It goes up 4,000 meters from sea level, and you'd think that was where the boundary. So that was one of the questions, was where is the boundary between East and West Antarctica, and does it matter to the ice shelf and its stability? So this kind of summarizes what I just went over, but it adds the additional overlay of there's volcanism underneath the both in the Ross Sea and beneath the West Antarctic ice sheet. Some of it's active today, and there's a real question of what is the feedback between erosion, sedimentation, and filling of that cavity, and how it in fact influence ice sheet stability in the long run. So those were our questions, is trying to go from top to bottom to see how those processes worked, and then how they interacted. And here's that question of where is that boundary and how does it affect what's going between East and West Antarctica. So as Renee and I were just talking about, the plane that we had been using to do airborne geophysics, unfortunately, is in the bottom of the Arctic Ocean, so it was no longer available to us. And at the same time, the members of the New York Air National Guard approached me and said, we have technology that we've used to, well, we won't tell you what we used but we have technology where we can install instrumentation systems on a C-130. And this is actually after the AGAP project into Dome A, where they realized that they had flown so much fuel into us that if they had had a plane with instruments on it, they could have done the whole survey with the amount of time they'd spent flying in and landing and giving us fuel. So they had this idea that you could take if you've ever been on a C-130, it has a cargo rail. You slide stuff in and out, and had an arm that grabbed onto the cargo rail and went out the paratrooper door where, in movies, paratroopers jump out the back. So we wrote a proposal and surprisingly got funded. It was the Recovery Act period when Obama was just elected and they were trying to invest in science. So we, partnering with the New York Air National Guard, took their system, which was for imaging. The other side was for shooting. We didn't do anything with the other side. But we took this and we, instead of doing it with infrared or whatever else they had, we put in the things that are probably more familiar with you. A LiDAR to measure the ice surface, visible and infrared cameras to look at structures in the ice surface, a shallow radar and a deep radar, so we can look at the structures near to the surface and then the ice thickness. And then we also had a gravity meter, one of my favorite potential fields, to measure the depth of the water underneath the ice shelf, and the magnetometers, because it's really useful to pin down what type of rock is there. And then, this is like no surprise to this company, this audience, we used Argo floats, air-deployed Argo floats, to see if we could measure the ocean properties in front of the ice shelf. So that was what we planned to do. And this is what it looks like before you put it in a C-130, basically a couple of racks of equipment. And then terrifyingly, you put your thing on a sled and take it out of the Jamesway, and then you thank everybody who did it. And then you hope that it goes on with the putting all your sensitive gravity meters onto a pallet and putting it in the back of an airplane. So it worked. And this is what the Ross Ice Shelf bed topography looked like beforehand. And what it was based on was measurements were made in the 1970s. That spacing where they went out and they set off explosives. So if you look at bed map 1 or bed map 2 and you want to know what the bathymetry underneath the ice shelf is, it's based on this. It's based on 1973 to 78. They flew out with an airplane and landed every half a degree and set off explosives to measure the ice thickness in the bed underneath. And that's all there is in all those compilations. And nobody had been back there since then. We planned and proposed flying a 10-kilometer grid over the whole ice shelf, which would give us significantly better bathymetry as well as insights into the geology and hopefully the oceanography and the ice structure. And that's what we ended up being able to fly was 55,000 kilometers. You can see it was harder to get the lines furthest away from McMurdo. That's why those are tend to be 20 kilometers spaced. So that was the plan. That was how we did it. What did we learn? Let's start with the bottom because that's the easiest, and we'll see how they mix up. You know, we're back to this question of, could we say anything about where that boundary was between East and West Antarctica, and did it matter at all? This is the magnetics. You may have, you know, studied magnetics and see how they're beautifully symmetric in the ocean. These are continental magnetics, so they aren't beautiful and symmetric. But there was a stunning signal in these, and you can see the dotted line is where people typically put the boundary between East and West Antarctica. And that's a color rendition. And you can see that that's not where, if you were to say there was a boundary between East and West Antarctica, where you would put it. You would put it running right down the middle of the Ross Ice Shelf and running down the middle of the Ross Sea. If you prefer to look at wiggles, if you were brought up looking at wiggle plots of magnetics, it's pretty clear that half of that ice shelf is underlaid by one kind of rock, not very magnetic, and probably thin continental crust, and the other side is much, much more magnetic. So that was really a major discontinuity there, showing that there are two sides of the Ross Ice Shelf. So what does that mean? Well, it means that when we go look at the gravity, it means that we can look at what the bathymetry is, but it means we have to correct for the underlying density. It's one of the real challenges is when you go from gravity. In the ocean, it's really easy. In the open ocean, most of the gravity maps we see assume one density, right? Because the ocean is pretty homogeneous. You can go from the gravity you measure in the ocean, and you get a pretty good estimate of what the bathymetry is. On land and over thin crust like this, you really have to get some sense of what the geology is, because otherwise you're going to end up with depths that are really wrong. So we were able to use those seismic measurements of depth to help us pin down the density for the inversion. The gravity's on the left, and you can see that the density ends up being really different too, and that the side that's toward the Transantarctic Mountain is much denser than the high magnetic on the left. So we end up suggesting that, you know, we really have two very different geologies underneath the Ross Sea. The high amplitude magnetics, low density, probably an accretionary province, you know, maybe something that where you can imagine what was put together when plates were converging, maybe an exposed core complex, but very complex convergent geology then stretched. Whereas the East Antarctic side is probably old cratonic material that's been thin, much simpler or relatively simpler history to it. We're ongoing, continuing to work where the sediments are and what the MOHO models look like. But what does that mean? That means that if you were to look at it in a cross section, as Christine Sidaway likes to do, we have half of it's transantarctic mountains and half of it looks like West Antarctica and looks like those mountains that exposed along marine birdland. So very different geology. So now what does that mean for our bathymetry? We're going to zoom in and look at what that density model we produced from that insight, and using the pinpoints from the 1970s, we're going to see what we can say about the bathymetry. Now we're going to jump back and forth a couple times. This is the 1970s version, the one that's in most available before the current bed machine came out. You can see the 50-kilometer spacing, and you see how there are little pock marks here. That shows you that it's all single points. But with the inversion of the gravity, you can see we have a significantly rougher and significantly different bathymetry, particularly near the grounding lines. And we'll zoom in and look at that in a minute. And you can see that there's the geologic boundary runs right through the middle of it. So let's look at it again. One of the big surprises for me was when I went to look at the grounding lines out of BedMap 2 and realized that they all had this beautiful, beautiful texture, right? You see how there's like swervy stuff in the bed. Now this is somehow they put in texture in a place that nobody had ever been. And it turns out what they decided to do was anywhere the ice shelf cavity got thinner than 100 meters, they decided they would put the texture from the ice surface down on the seafloor. It's like, what? Anyway, guess what? You'll be shocked to hear that's not the way it is. So if you ever see a map that has beautiful texture on an ice shelf near a grounding line, be suspicious. Ask how it got there, because it's really unlikely that they were able to get that beautiful texture in any way that I know how to do very effectively. Maybe if you, I don't know how you do it. Anyway, so you can see that we resolve deeper grounding lines in general around the Ross Sea by measuring it as opposed to inferring it from the surface texture. And so what we argue is that the bathymetry is now steering, this new bathymetry is steering the circulation underneath the ice shelf. So we're going to take a look at the oceanography and the different packets of water we looked at. This was, again, one of these things where you're thankful you can get different funding streams in the US. This was actually funded by a foundation who decided that we should actually measure the ocean and allowed us to deploy the LMO floats that aren't as robust as the Argo floats most used here, but at least they got us one season's worth of data. So we were able to deploy 6 of them in front of the Ross Ice Shelf. And this made us really good friends with the Guard. If we weren't good enough friends, the New York Air National Guard loves throwing things out the back of airplanes. So if you want to make friends with pilots, let them throw stuff. So these are the different, but what was nice is we ended up seeing the very classic water masses that you think about when you think of ice shelf stability, and particularly in the Ross Sea region. You can see the Antarctic surface water, the modified circumpolar deep water, the water that is certainly what's pointed towards in the Pine Island and Thwaites region as being the trigger for the change. Ice shelf water from the melting of the ice shelf, and then high salinity shelf water, each with their distinct characteristics. So we're going to look to see where our ocean models would suggest they go now that we're looking at more realistic topography underneath. So this is the high salinity shelf water. And you can see that it goes in and pretty much fills the cavity on the East Antarctic side. Doesn't seem like it reaches the West Antarctic side much at all, but it fills the cavity. So if we look at it in cross section, it means on that side, that side has high melt rates, but pretty stable from that water mass. And whereas the other side, on the West Antarctic side, there isn't much of that water getting in there. There's very little circulation and very low melt rates. So we also looked at the grounding line, both before and after. You can see this is if you ran around the edge of the ice shelf, you can see that it's deeper in our new presentation on the East Antarctic side, and it's variable on the West Antarctic side. Some places it's deeper, some places it's shallower, but it still means that there's very little circulation on the West Antarctic side, and you can see that geologically it pretty much falls out that the West Antarctic side is where the ice shelf is thinner and there's less circulation. East Antarctic side is a much bigger ice shelf cavity. So then let's go look at the next water mass, the modified circumpolar deep water, the one that's coming up over the shelf. You can see it tries to get in on the East Antarctic side in that close to the boundary, a place where there is a nibble in the ice shelf, but doesn't seem to get very far in. The New Zealanders claim that they've identified some where they were drilling near the grounding line. I haven't seen those results yet, so that'll be interesting to see, what the pathway might be for this water to get to the grounding line. But we don't think that it's easy for it to get there. But what we did see was a lot of this Antarctic surface water forming through the season. This is across, from when we dropped it in December through to when it iced up in February. And you can see that this thick upper warm layer formed. And what surprised us is we actually ended up being able to see the impacts of how this warm surface water was impacting the ice shelf. Again, sort of pointing to, let's look first where it goes, and then we'll look to see how, by bringing this interdisciplinary team together, we were able to say, okay, can we see the impact of that water on the ice shelf, and can we tell you how long it's been there? So here's the model of where the Antarctic surface water forms, and I want you to look over here on the right-hand side, right over towards Ross Island and Mount Erebus, and what you see is it forms and it nips in right there every so often, right? About once a year, it forms and it goes in. And what you can see is it's going in right here where you see this high tongue of melt. On the left-hand side, we have high melt rates predicted. And that's what the model also suggests. It's actually this summer water that's melting the ice shelf. Do we see any evidence of that in the radar? Even though I've already made you look at radar in East Antarctica and in Greenland, you can probably guess I like looking at radar. This is a cross section at the bottom across the ice shelf. And it doesn't show up here because I can't make it big enough, but each packet coming out of each ice stream and each outlet glacier has a unique signature. So you can track it across the ice shelf. You can watch it getting buried in the snow. It's really just an exercise in stratigraphy. And you can see by using our radar, we can actually watch what's happening over time when we correct it for how fast it's moving and what's happening to the bottom, because we have this point we know is fixed. So just to those of you who haven't looked at radar a lot, here's the ice surface, right? Very flat. This curvy structure is the ice bottom, right? It's about 200 meters here and about 400 meters here. This is the ice that came out of Bird, and this is the ice that came out of Mullet Glacier. And what we're gonna do is we're standing close to Ross Island, and we're gonna step forward 20 kilometers at a time, and you're gonna see what happens to the bottom of the ice shelf. And here we go. We can track what happens to the surface, so we know what we can correct for the thinning and we can correct for the accumulation. And what you can see is that package of ice out of Mullet just disappears. We're going to go back once more just in case you don't believe it. So here's the package of ice that came out of Mullet. this snow fell on the ice shelf. And then as it flows forward, as if I was flowing towards you, you can actually see the base of the ice shelf getting higher and higher. And what that tells us is this process that we're seeing now of surface melt that you can map with altimetry has been stable for 82 years at least. So the processes we're seeing now have been active throughout this century. So, and you can then actually, if you want, make a map of the melt using radar over the entire ice shelf, giving you a sense of the long-term melt history. And you can see that the place that's really been melted is the place right next to Ross Island. Does that matter? Let's look. So we know that, we'll come back to that. Well, we know that the grounding line rates are high. They're done by the high salinity shelf water. We know that West Antarctica is, the cavity is mostly filled by ice shelf water. Some near the front, modified circumpolar deep water, but not getting to the grounding line. But the melt is being done in the top right by this Antarctic surface melt water, right there. And what's interesting is there's this concept on ice shelves that there's a place they're vulnerable. If you can take off the icebergs and it doesn't matter. You can do stuff to the front of the, most of the front of the Ross ice shelf and it doesn't matter. But there are places where if you remove that ice, it's going to have an impact on the glaciers behind it. And it turns out that this place is outside of that safety band in the front. It actually is one of the places that it matters. So in the long run, you know, it will be interesting to see what happens if we change the production of surface melt and increase the melt in the front, and it has the potential to impact the West Antarctic flux. So again, looking at how something way in the front may impact the grounding lines 800 kilometers away. So just one other reflection, since we do have people who think about paleo, we have to remember that the predictive models are constrained by ice cores, but the ice cores, sediment cores, and what's happened in the past. But we have to make sure that the processes that are in those models are processes that are actually happening. We argue that there probably has been this shift over time on these large ice shelves, and this might matter from East Antarctica, where at one point the circumpolar deep water was able to access the base of the ice shelf, like what's happening in Thwaites and Pine Island now. But as that ice grounding line retreated, there was a change in which water masses were controlling the grounding line, what water could actually reach the grounding line, and what part of the ice shelves were susceptible. So, including in my ROSETTA piece, you know, the tectonic boundary seen between East and West Antarctica controls the bathymetry that is steering the circulation. And it looks like the present day ice-ocean interaction is actually driven by local water masses, with the vulnerability being surprisingly at the front and not back at the grounding line. And this analysis suggests that over time there's been a change in processes where initially when you had the grounding line close to the MCDW, that would have been what we all carry in our head was the control. But over time, as you filled the cavity with ice shelf water, you shifted the vulnerability to the front. So it's, again, a very sort of integrated approach at looking at this. So where does it get me to thinking about East Antarctica? You know, one of my goals being here is seeing if I can foster or just help the conversation about how we build international collaborations to look at changing ice in East Antarctica. How can you really bring together the disciplines? Because I hope you get a sense from this ROSETTA approach is that by having the multiple disciplines at the table and thinking about it, we actually had the real conversations between the geologists and the oceanographers and the glaciologists about what the interactions were, how the bathymetry was driving the flux, what that really, where it mattered and where it didn't. And we were lucky there was a great big signature down the middle of the ice shelf that really prompted the conversations. But how can we learn, or how can we sort of bring a similar approach of looking at it together to identifying the glaring knowledge gaps that we all need to address if we're going to know how East Antarctica is going to change in the future? And also, how can we use our lessons, sort of virtual and hybrid collaboration we learned in the pandemic to build collaborative networks? Because I certainly know that from the US side, NSF has said they really want the next stage to involve, mid-career scientists. They want to figure out how to build strong mid-career networks to help move this forward. So that's also on my list of, I love ideas on how to do that. Do we take all the people who graduated from APEX? As I like to think of the APEX graduates. Are they ready to be people who lead now? So this is just sort of, my thoughts on this is that can we figure out how to make that compelling case for East Antarctica? Because I know how to do it for West Antarctica, but I'm not sure, I'm still struggling on how to make it for East Antarctica. We know there are observed changes. We know the surface is lowering. Right? This is, Icepod 1 to Icepod 2. You can see the red blob. We know the ice shelves are thinning wherever they're red. This is just Robin's awful PowerPoint, so apologies, but you get the ideas. We know the velocities are increasing. We know if we correct those velocities for surface accumulation, we can see that the discharge is increasing. We know that GRACE is showing us mass loss in those very similar places. And we know that when our sense is it's the ocean heat shifting that is bringing in that paradigm of bringing the heat closer to the grounding lines. And we certainly see this, the heat shifting south and also showing up in closer to the large outlet glaciers like Totten and Denham. So that's what we can observe. The question is, could we come up with a compelling case of what are the interconnected layers of vulnerability? How can we have a conversation across discipline about what they are? Another ugly Robin PowerPoint animation, but just to get you to think, what is the grounding line geometry? How does the geology control the geothermal flux, the faults, and the sediments? It matters where the water underneath the ice sheet is. It controls how fast it's going to flow. Where is it sticky? Where is it slippery? How fast will that flow in the future? Where is it vulnerable? What do we need to know? Where's the accumulation going to change? That's clearly important, both from the GRACE observations and from the how you see the change in pattern between change in velocity and change in discharge. Accumulation is going to be very important in the future. Increased ocean flux. Will that heat reach the ice shelves? And then which are the actual ice shelves that are vulnerable and which ones actually matter? Now that we saw that at the Lost Ice Shelf, it didn't actually matter if you took it off most of it, but there are places that are vulnerable. So this is just an example of sort of what I'd like to see if we could put together sort of a, what are the compelling observed changes and what are those interconnected layers of vulnerability as a way to bring people together and see if we can start to have those real interdisciplinary conversations about building future collaborations and prioritizing where we work. So I'm looking forward to ideas on how to do this. Beginning to have a concept of maybe we have a one-day workshop in the second half of March, just to sort of start moving these ideas around. I know there's lots of other work going, but this could just be a beginning conversation on, how do we tighten our articulation and build the shared language and the networks that we now need to collaborate. So thank you very much. And I appreciate you letting me talk about so many different things. And I really have shown the work of a lot of different people. And I'm really just here as a spokesperson. It's been funded by a lot of different agencies and foundations, and also the work of many people, and I'm really just here as the spokesperson. So thank you very much for having me speak today, and I'm happy to entertain questions. I will, or can change it if I don't like it. I don't understand it.
You pointed out that at the last glacial maximum, the water gave into the ROSETTA shelf cavity was quite different. Is that because the ice was so close to the shelf, the shelf was narrow, so no proximity to water?
Right. That's really the crux of that argument, is that the ice shelf would have been since you would have had the grounding line so close to the shelf edge, it would have been a lot easier for the offshore water to reach into the cavity. It would have been a much smaller cavity. It would have been more like an East Antarctic cavity.
Thanks very much, Robert. On that particular diagram, you've got the linear there. Have you given any thought to the variability in the linear dynamics and the way it's affected by changing katabatic winds in the atmosphere, etc., and how that plays into this whole system?
As you can imagine, we argued about that a lot. Okay. Oh, sorry, I didn't repeat. The first question was about how this, what the fundamental difference between last glacial maximum and the present in terms of access, and it really is the proximity of the grounding line to the continental shelf and therefore the CDW. The second question is, how is the Plinia impacted by what role does variation in the Plinia play in this? And that is one of the things that we think may play a role, is that suddenly this means that the katabatic winds and the formation of the Plinia and filling this cavity with that high salinity shelf water is in essence buffering the grounding line from the NCDW. So it is a way of thinking how connected the atmosphere is, what's going on to the grounding line. So yes, there's probably variability, and it's certainly something we've argued about.
Yeah, thanks, Robin. That was really cool. Just to go back to your other statement, interested of community building. One thing was obviously the impact not only on the field trip, but also on the momentum of the scientific community during COVID. And actually, I think a lot of positives came from some of the side effects of COVID, like our digitization and Zooms and all this. So how do you see that going forward, especially also in a more geographically distributed approach?
I agree with you. I'm trying to show you that. Okay, so the question is, what do I think the future of collaboration is? I've lost control of this. I think the lessons that we've learned from the pandemic, and how is that going to help us move forward? I mean, I watched during the pandemic I know we're all tired of Zoom, and some days we think I can't do another Zoom call. But what it has done is it's allowed us to participate and us to build networks we couldn't do before. And, I was going to try and find my Greenland example, because to me that is sort of the extreme, in that it was originally going to be just us going there a couple times a year and going to communities. Sorry, I can't make this slide. You go full screen. I can't figure out how to do it. And talk simultaneously. But thank you. This to me was one of the most beautiful things that happened in the pandemic, was that instead of NSF-funded scientists from an elite Ivy League institution going to communities we actually ended up building a more honest, equitable partnership where it was our Greenlandic partners who did most of the work in the communities. We participated by Zoom. That we ended up with young Greenlandic women doing the multi-beam mapping, thing that just about makes me cry, right? And that we had them going back to their communities and explaining glacial isostatic rebound, right, to their parents who are fishermen. And it ended up being, you know, news in Greenlandic on the big Nuuk newspaper. So to me, that, in terms of participating with communities, to me, it taught me a lot about being humble and making sure to empower your local partners in a way that I hadn't really, it wasn't the way we wrote the proposal. But I think in terms of scientific collaborations, I think there's similar lessons to be learned, is that we have to make sure we, and this is where I'm back to the mid-career people who may not be as likely to travel, but we have to make sure they're at the table when we're designing the experiment, not just bringing them in later on, that we need to make sure that we build those collaborations so that they can be there writing the papers when we collect the data. So there, that was a really long answer to your short question. But I think it's real. I think we've learned a lot, and I think we have to be careful not to let sort of the fatigue, and I will admit, being here on the other side of the planet, I now appreciate how hard it is to be here and participate in meetings there. So good on you for doing this all the time. Yes.
Sorry, I just tried to think what the analog to Greenland was, and I thought it was communication to the wider Australian taxpayers who fund most of our science, and importantly to the decision makers. Do you have a golden solution to cut through to them? What can we do, and especially what can, as you say, the PCRs and MCRs do better than?
I think some, you know, the question is how to better communicate to both the people who fund us and the policymakers. I think we take every opportunity we can to speak. I think we figure out how to put our science in even simpler terms. You know, that's why I'm after this. That's why I'd love to have this conversation about how we describe the change in East Antarctica. When I talk about West Antarctica, I say that I can say it with pretty much just waving one arm. I can say it's speeding up. It's like mozzarella cheese. So it's stretching and getting lower, and we weigh how much it weighs, and it's less of it. We need to practice those or figure out what they are so that we can communicate simply about what the change is and how to get them to value it. It's a long haul, right? And we've seen change, we've seen improvement, and I think we just have to keep on trying. Okay, I'll do one more plug. AGU actually does have programs where they work on, and I don't know whether it applies to international people, but if you ask them, they're more likely to try and figure out how to do them. But they bring people in and train them in terms of how to communicate better with policymakers. And then they go back as a cohort and commit to communicating on a frequent, you know, say once or twice a month with people in government where they live. I think it might be just in the US, but if there were people internationally who were asking for that program to be expanded, then I think AG would listen. So I think, you know, take every opportunity you can, and if it's not, doesn't apply internationally, ask for it, right?
East Antarctica, I agree, is a problem. On bedrock, East Antarctica, I think it had a bit of a change, trying to guide, but still better that a gap in knowledge along with a few other things happening. Trying to be very specific.
I'm not quite sure. I think there are huge gaps. I mean, when we published a paper in 1990 about there being a volcano underneath West Antarctica, we had to remove the line saying that West Antarctica could change rapidly. So we've seen a change even in our own community. And I would argue that we still don't understand. I think that there's still a lot of work to be done in that ice rock interaction piece, and we need to better understand what the rock is. And then we need to make sure we actually build that knowledge of how to put what we know about the substrate into ice sheet models, because that's still a gap, I think, that we need to address. Is it's, you know, we know in weather models, they have classification for different types of terrain. We need to figure out what the informed way to do that of what the underneath the ice sheet is and how that informs the ice sheet behavior. Yes. Sure. No, I'm happy to. It's okay. We all have this notion that water runs downhill, but when you put an ice sheet on top of a river valley, right, and the ice is thinner at the top, you actually, basically it's like jumping on your hose. You're squirting the water up the hill. So you've actually changed the overlying pressure by having the ice sheet slope in the opposite direction to the river valley. In all around the Gambler's Mountains in East Antarctica. It happens in some Alaskan glaciers. And then you tend to get, you know, when you drive the water up to where the thermal gradients in the ice are sufficient, that's when you refreeze it on. And that's, you know, it is actually that water that's gotten driven up to where the ice is thin and cold that then refreezes on in that giant blob. And it probably is happening with water falling through the holes on the rim of Greenland, but nobody's drilled any of these, so nobody can prove me wrong yet.
I remember when that came out, showing those pictures, there was one report about potentially that means you could get old ice, summer ice. Do you have any sort of thoughts on whether you think they could be old ice that's easily accessible?
That's my dream, is that, you know, so the question is there old ice pushed up by one of these features? Because if you look at this radar image on the right, you can see that ice that would have been at the base of the ice sheet is now, that would have normally been about at least 2,000 meters down, is now within about 1,000 meters of the surface. So I think it's possible. I'd want to do a lot more radar before I moved my drill there and sampled it. But you know, you could make a lovely case that you could try for old ice and to answer the question of what these are made of. One hole, two things.